Ready? Let's get to it. In 1977, NASA launched two spacecraft on a mission designed to last 4 years, study Jupiter and Saturn, snap some photos, call it a day. That was almost 50 years ago. Both probes are still transmitting, and what they found out there rewrote the textbooks, starting with the very edge of our solar system, where the sun's influence runs out and something no one predicted was waiting. Number 8, the traffic jam at the end of everything. For decades, scientists assumed that constant stream of charged particles blasting out from the sun at a million miles per hour simply faded away the further it traveled, like a shout dissolving into silence. Makes sense, right? The further from the source, the weaker the signal. Voyager proved them wrong. As both probes pushed past 11 billion miles from the sun, their instruments picked up something nobody had modeled. The solar wind wasn't thinning out, it was piling up, compressing, slamming into something it couldn't push through, like a river hitting a dam it didn't know was there. That dam is the heliopause, the absolute edge of the sun's influence. And at that boundary, all those charged particles that had been racing outward for billions of miles suddenly had nowhere to go. They collided with interstellar plasma flowing in from the opposite direction. Imagine every car on every highway in the world trying to merge into a single lane at the same time, except with superheated plasma moving at hundreds of kilometers per second. But here's the thing, this wasn't just particles slowing down. The density at this collision zone spiked. The temperature surged. Everything the sun had been throwing into space for millions of years was backed up into a chaotic, churning boundary layer, a thin shell of superheated plasma separating our solar system from the rest of the galaxy. Before Voyager, nobody knew this shell existed. We thought the solar system just ended. Instead, it's wrapped in a wall of its own exhaust, a compressed ring of fury marking the line between us and everything else. Number 7, the invisible wall. On August 25th, 2012, Voyager 1 was coasting through the outer reaches of the solar system when its instruments registered something dramatic. In the span of just a few hours, the count of charged particles from the sun plummeted, a 1,000-fold drop. Simultaneously, in galactic cosmic rays, radiation pouring in from distant dying stars surged by 9%. Voyager 1 had crossed the heliopause. It had left the building. What stunned scientists wasn't that it happened. They'd been expecting it for years. What stunned them was how it happened. The transition wasn't gradual. It wasn't a slow fade from solar influence to interstellar nothingness. It was a cliff. One moment, Voyager was bathed in the sun's particles. The next, it was swimming in galactic radiation. Imagine walking through your house and suddenly stepping into a different country. No border crossing. No transition zone. Just different. 6 years later, Voyager 2 hit the same wall in November 2018 and confirmed it. The heliopause isn't a fuzzy gradient. It's a hard boundary, a physical edge where the sun's dominion ends and the interstellar medium begins. The solar wind flows along the inside of this boundary. Interstellar plasma presses against the outside. Two oceans of charged particles, nose to nose, holding each other at bay across a border thinner than anyone imagined possible at that scale. We always talked about the edge of the solar system as a metaphor. Voyager showed us it's not a metaphor, it's a place, and it's sharper than a knife. Next time you look up at the night sky, remember, there's a wall out there. You can't see it, you can't feel it, but it's the only thing standing between you and the full fury of galactic cosmic radiation. And two little probes the size of compact cars are the only reason we know it's real. Number 6, the shield that won't stay still. So we've established that the heliosphere, the sun's protective bubble, has a hard edge. But here's what Voyager data revealed next. And it's arguably stranger. That edge moves. Not slowly, not in a predictable orbit. It writhes. Scientists analyzing data from both probes discovered that the surface of the heliosphere is distorted by massive rippling waves, appearing at unpredictable, non-uniform angles. Some of these waves stretch across 10 astronomical units. That's 10 times the distance from the Earth to the Sun, roughly 930 million miles from crest to trough. Picture the bubble that protects your entire solar system. Every planet, every moon, every asteroid, breathing in and out like a living thing. its skin bulging and warping as invisible forces crash against it from the outside. What makes this truly unsettling is that Voyager 1 crossed the heliopause in 2012, but Voyager 2 didn't cross until 2018, 6 years later. Both probes were traveling at similar speeds. Both were heading outward. The gap should have been much smaller. The reason? The boundary itself had shifted. Between 2012 and 2018, the heliosphere's edge had moved, possibly by billions of miles. The sun's shield is in constant flux, expanding and contracting in response to solar activity and the pressure of interstellar wind. We don't live inside a static shell. We live inside something that pulses, expanding when the sun is active, contracting when it's quiet. On one side, it's blunt, compressed by the direction the sun travels through the galaxy. On the other, it stretches into an enormous tail, less soap bubble, more cosmic jellyfish. And the models we built before Voyager can't explain the speed or scale of these changes. Not even close. Number 5, the energy that vanished. When astrophysicists modeled what would happen at the heliopause, where the solar wind finally decelerates to zero, they predicted a sharp spike in both temperature and particle density. It made perfect sense. All that kinetic energy from billions of miles of solar wind has to go somewhere when it slams to a halt. The math said the boundary should be blisteringly hot and incredibly dense. Voyager got there, took the measurements, and the numbers were wrong, not slightly wrong. The temperature and density readings came back 10 times lower than the theoretical predictions. 10 times. That's not a rounding error. That's a fundamental gap between what we thought we understood and what's actually happening. So where did the energy go? This is the part that keeps plasma physicists up at night. The solar wind carries an enormous amount of energy outward. It hits the heliopause and decelerates. The laws of thermodynamics say that energy has to be conserved. It has to transform into heat, into pressure, into something. But Voyager's instrument said, nope, most of it just isn't there. Some researchers think the energy is being absorbed by processes we haven't identified yet. Perhaps magnetic reconnection events or interactions with interstellar dust that our models don't account for. Others suspect we're fundamentally misunderstanding how plasma behaves at these scales. The worst part? This isn't just a Voyager problem. If we're wrong about how energy dissipates at our own solar system's edge, we're probably wrong about every other star system too. Every model of stellar winds, every calculation of how stars interact with interstellar space, all of it rests on assumptions that Voyager just quietly demolished. Number 4, the void that gets thicker. Interstellar space. The void between stars. When you hear those words, your brain fills in the picture. Emptiness. Cold. Nothing. And for the most part, that instinct is right. The density of particles out there is absurdly low. Inside the solar system, near Earth, you'll find about 3 to 10 particles per cubic centimeter. At the heliopause, that drops to about 0.002. So when Voyager 2 pushed past the boundary and measured the particle density of interstellar space, scientists expected a very small number. Their models predicted roughly 0.037 particles per cubic centimeter. And sure enough, the first reading came back at 0.039, almost perfect. Then Voyager kept flying, and the number started climbing. At 124 astronomical units from the Sun, about 18.5 billion kilometers, the density had tripled to 0.12 particles per cubic centimeter. Interstellar space was getting denser the further Voyager traveled from the Sun. That's backwards. That's not supposed to happen. Here's the kicker. We still don't fully understand why. The leading hypothesis points to the interstellar medium itself. The plasma, dust, and magnetic fields between stars may not be the uniform sea scientists assumed. It might be lumpy, patchy, structured in ways we've never been able to measure because we've never had an instrument out there before. Others suggest the increasing density is related to the outer boundary of our local interstellar cloud, a warm pocket of gas that the sun is currently drifting through. We might be approaching a denser region of this cloud, or even its edge. Either way, the empty void between stars isn't empty. It's layered. It has texture, and it gets thicker the deeper you wade into it. That one discovery alone rewrites assumptions about interstellar travel, about how stars interact with the space between them, and about what's really waiting out there. Number 3, the magnetic field. That shouldn't be that strong. Before Voyager left the heliosphere, scientists had a rough estimate of the interstellar magnetic field strength, based on indirect observations, how cosmic rays behaved, how the heliosphere seemed to flex. They arrived at a number, and then Voyager 1 flew into interstellar space and measured it directly for the first time in human history. It was 2 to 3 times stronger than predicted. Now, a magnetic field that's 2 to 3 times more powerful doesn't just mean slightly more magnetism floating around. It means the interstellar medium is pressing against our solar system with roughly 10 times more pressure than anyone had calculated. 10 times. The galaxy is pushing against us far harder than we thought. What makes this particularly disturbing is what it implies about the heliosphere's stability. Our sun's magnetic bubble, the thing that shields Earth from the worst of galactic cosmic radiation, is under significantly more siege than our models predicted. The heliosphere is thinner, more compressed, and more vulnerable than we assumed. That cascade of recalculations extends outward too. If we were wrong about our own backyard, we're almost certainly wrong about how every other star in the Milky Way interacts with interstellar space. Every stellar model, every exoplanet habitability assessment that factors in stellar wind protection, all of it needs revisiting. A single measurement by a spacecraft running on less computing power than a modern digital watch just forced astrophysics to rethink its assumptions about the entire galaxy. Number 2, the bubble inside the bubble. So here's something that will rearrange the way you picture our place in the universe. We've been talking about the heliosphere, the sun's protective bubble, about 11 billion miles across. But Voyager's data, combined with decades of research it helped inspire, revealed something much bigger. The entire solar system, heliosphere and all, is floating inside a second bubble. Cosmic void, roughly 1,000 light years in diameter. Scientists call it the local bubble. About 14 million years ago, a chain of roughly 15 supernovae detonated over several million years in our galactic neighborhood. These explosions didn't just scatter debris, they blasted interstellar gas outward like a shockwave, hollowing out a massive cavity in the Milky Way. The result is a region of extremely low density space, nearly a void, surrounded by a compressed shell of gas and dust where new stars are actively forming. Our sun wasn't there when it happened. It was roughly 1,000 light years away, but about 5 million years ago, as it orbited the galactic center, the sun drifted right into the middle of this ancient explosion site. And today we sit almost dead center in it. But here's the thing, this bubble isn't just a fun piece of cosmic trivia. It's the reason we can see the universe at all. If the space around us were as dense as the average interstellar medium, many of the stars we observe would be invisible. Our view of the cosmos, the one that launched astronomy, that drove us to build telescopes, and that ultimately put Voyager on its trajectory, exists because we happen to live in a cleared out pocket of the galaxy. And here's the darker implication. Researchers have found that every time the sun has crossed through one of the galaxy's dense spiral arms over the last 500 million years, it lines up with a mass extinction event on Earth. 5 known mass extinctions, 5 arm crossings. The correlation is chilling. Right now, the sun is coasting through quiet, low-density space between the Sagittarius and Perseus arms. The local bubble is essentially a harbor, a safe haven carved out by ancient stellar explosions that, by pure coincidence, we drifted into just before our species appeared. We're inside a protective void, inside a protective bubble, on a planet with a magnetic field. I'm orbiting a star in a quiet stretch of the galaxy. The number of shields between us and oblivion is staggering, and we only know about most of them because 2 small probes launched in 1977 refused to stop sending data. Number 1, the hum from the void. Voyager 1 is currently over 15 billion miles from Earth. At that distance, a radio signal traveling at the speed of light takes more than 22 hours to reach us. The probe is powered by decaying plutonium, running on a computer with 69 kilobytes of memory, less than it takes to store a single photograph on your phone. Most of its instruments have been shut down to conserve what little power remains. But the plasma wave instrument is still listening. And in 2021, it picked up something that changed the way scientists think about interstellar space. A hum, faint, persistent, steady at approximately 3 kilohertz. not a burst, not a spike, a continuous, droning vibration in the plasma of interstellar space, holding its frequency with eerie consistency for nearly 3 years straight. Now, technically, there's no sound in space, not in the way we experience it. There aren't enough particles for sound waves to propagate the way they do on Earth. But electromagnetic waves travel through vacuum just fine, and Voyager's instruments can detect oscillations in plasma density and convert them into data. When scientists translated that data into audio, what came out was a low, haunting drone, the background noise of the universe itself. Most researchers believe the hum is generated by plasma waves rippling through the interstellar medium, the faint vibration of charged particles drifting between stars. It's the ambient sound of the galaxy, a frequency so constant that Voyager detected no meaningful change even after traveling another billion miles. The real nightmare fuel is this. Some scientists aren't satisfied with the plasma wave explanation. The level of consistency, the sheer uniformity of the signal across such an enormous stretch of space, suggests there might be an energy source sustaining it that we haven't identified. Something out there, in the dark between stars, is vibrating the fabric of interstellar space at a single, unwavering frequency, and we have no idea what it is. Voyager 1 is dying. Its power supply drops by about 4 watts every year. Within the next few years, it will fall silent forever. Both probes will drift on, unpowered, carrying golden records etched with greetings in 55 languages, music from Beethoven to Chuck Berry, the sound of a mother kissing her newborn child. All of it sailing through the dark at 38,000 miles per hour toward stars they won't reach for 40,000 years. But the hum will continue. It was there before we arrived. It'll be there long after we're gone. The interstellar medium will keep vibrating at that quiet, steady frequency, whether anyone is listening or not. Voyager just happened to be the first thing we ever built that got far enough away, stayed alive long enough, and listened carefully enough to hear it. And now, so have we. If this blew your mind, we've got more coming. Subscribe so you don't miss the next one. See you there.